So today we're going to start by talking about limits, the theories around limits. The limit is an analysis of a behavior of a function near a particular input. So let's start by looking at how to find limits based on a graph. So if we're looking at this graph of y equals f of x, and here's our function graph, we're going to start by looking at how to find the limit as x approaches 2 of this function. So we're going to find x is 2. So here's x is 2. So once we've found that, we're going to trace back our function from either side, from the right side and from the left side, and we're going to trace them all the way back toward x equals 2 until our two colored pencils, they touch. And right here, where they touch, where this green point is now, is going to be the numerical value of the limit as x approaches 2. So in this case, as x approaches 2, the numerical value would be negative 2.25 based on this graph. So right here, we're going to put a negative 2.25. So once again, we'll go over that one more time. So you're going to go find the x equals 2, and you're going to go take your left-handed and your right-handed sides, and you're going to trace all the way back until you find where your two colored pencils touch, or your two fingers if you're using your fingers. So next we're going to try the limit as x approaches 0 of f of x, so of this function. So one more time, we're going to locate 0. We're going to take our right and our left hands, and we're going to trace all the way back along the function until our fingers touch. So the limit as x approaches 0 of f of x is right here where my green colored pencil is again, and that would be equal to 2. As you can see, we're looking for the y value of this function as it approaches a particular point. So let's try another one. Limit as x approaches negative 2 of the function. So here we go, we're locating negative 2, and we're going to take our fingers, or our colored pencils, put them along the points, and go all the way together until they meet. And here they meet at about negative 1.75 on our graph, right about here. So see where this green hole is? That's at about negative 1.75. So that's the answer to the limit. However, as you see, there's a hole here. So when there's a hole, that's the limit still exists as we have come together and our pencils have touched in the same area, but the limit of f of 2 equals, it would be negative 1. As you can see, there's a filled in hole right where my blue colored pencil is. So therefore, it would be equal to negative 1. So f of 2 equals negative 1, but the limit as x approaches negative 2 would be this negative 1.75. So one more time, the limit, or the f of negative 2 would be negative 1. All right, let's do another. Limit as x approaches 3 of f of x. So we're going to go over here to 3. We've located 3. And we're going to go and we're going to trace our points leading up to 3. And our fingers have ended up in different places at x equals 3. So therefore, the limit does not exist. When our fingers pass each other like this, or our colored pencils, and they don't touch up at a point like they did at, per se, x equals 2, how they touched here, if they don't touch, it means that the limit does not exist. So the limit as x approaches 3 of this function does not exist. So what we do in this case is we take a handed limit. So what we're going to do is we're going to take the right-handed limit and the left-handed limit, and we're going to figure out from two different sides what the limit as x approaches 3 is. So let's start with the limit from the left-handed side. So the left-handed side is just marked with this little negative up at the top, so it's x approaches negative 3 from the left side with this little negative up here. So from the left-hand side, we're only going to use our left-hand pencil, and we're going to trace all the way up, and as you can see, it continues to grow bigger and bigger and bigger as we approach 3. Therefore, the limit as x approaches 3 from the left would be infinity, positive infinity. Now, if we want to take the limit of this function at x equals 3 from the right, we're going to trace it back from the right all the way over here to this hole like we saw at x equals negative 2. Therefore, this hole is at negative 2 on the y-axis, so the limit of this function as x approaches 3 from the right would be negative 2. Okay, now let's talk about some horizontal and vertical asymptotes. So these are like imaginary lines per se of that, like the function doesn't usually cross over. Horizontal asymptotes, they can cross over. Vertical asymptotes, they do not cross over whatsoever. So let's start with our horizontal asymptotes. As you can see, it's a line right, there's a line, imaginary line right here that this part of our function doesn't cross over, and this line is at y equals negative 2. So this imaginary line is what we call a horizontal asymptote. So it's y equals negative 2. And there's the same imaginary line at the same y value over on this side as well. So we're also going to make it on this side. But as you see, since we've talked about how a function can cross over a horizontal asymptote, you can see here that this horizontal asymptote has been crossed over in this function right here. But on this side, it is not crossed over, and it is approaching negative 2. So that's what the horizontal asymptote is. It's just a number of imaginary line that the function approaches as it goes off. Now, for vertical asymptotes, these cannot be crossed over. So therefore, you won't see it crossed over whatsoever because of the vertical lines. So there's an imaginary line here at x equals 3. As you can see, it doesn't cross over. X equals 3, the function is approaching from the left-hand side. It approaches x equals 3, but it never crosses over it. And then the same thing, there was a point of discontinuity where the function has changed and the graph does not exist, as we talked about right here. Therefore, this has become a vertical asymptote at x equals 3. All right, now let's try this function and trying to find the limits of certain points using this function. All right, so let's start with the limit of this function as x approaches negative 1. So here we go. Let's once again locate negative 1, take both of our fingers and trace all the way back, and we're getting a negative 2 is where our pencils meet. So therefore, the limit of this function as x approaches negative 1 would be negative 2. Once again, there's a hole here. As you can see, I'm coloring it in green. There is a hole. However, it doesn't cause a point. It doesn't cause the limit to not exist because our fingers still touch in the same spot. So the limit as x approaches negative 2, so here we are at negative 2. As x approaches it, we're getting a negative 1. So we should be getting a little bit faster at this since we are practicing, and we had already gone over the first example. So let's try as x equals 0. So let's trace our fingers back after locating 0, and we don't end up in the same place. Therefore, the limit does not exist. Does not exist. And this is because our fingers didn't end up in the same place, and there is a point of discontinuity. Also, so now, the limit as x approaches negative infinity, so let's locate x approaches negative infinity, would be all the way over here at my blue pencil. And as you can see, it is fluctuating around the line of y equals 0. It's fluctuating, but it's getting closer and closer to that point. Therefore, the limit as x approaches negative infinity of this function is actually 0. Because it is approaching that line, it's fluctuating over and under it, but the points are getting closer and closer to the point of 0. So now the limit as x approaches infinity would be all the way over here at my green pencil, going this direction and all the way off the paper, obviously. This is approaching the line of y equals 1. So for the limit as x approaches infinity, it would be approaching 1. All right, now let's talk about handed limits. As I said, this little negative mark over here means it's from the left, and the positive mark over here would be it's from the right. So let's talk about the left-handed limit of as x approaches -1 of this function. So now we're only going to use our blue pencil. And we're going to take it and we're going to trace all the way back, all the way back, all the way back, all the way back, and we're getting -2. So now if we want to take the limit of this function as x approaches -1 from the right side, we're going to take only our right colored pencil and we're going to trace all the way back until we get to x equals -1, and again that's going to be -2. So right here we would put a -2. So now we're going to do the limit of f of x as you approach -2 from the left. So now, again, here's -2. We're going to locate it. We're only going to use from the left. And once again, we're going to get -1. -1. Now, when we're trying to find the limit of this function as we approach 0, that's when we need the handed limits. For the first part, or for the most part, right here, they've been the same as originally. However, when we get to x equals 0, that's when we need these handed limits. So when we're trying to find the limit of this function as x approaches 0 from the left side, we're going to only go on the left side and we're going to trace our function closer and closer to 0, and as we can see, it's getting closer and closer to positive infinity, which would be all the way up here. So we're only going to use our left side, and we're going to see that as it approaches 0 from the left, it's going to be going to positive infinity. Now we're going to do the same thing for the right-hand side, only using our right colored pencil, and we're going to trace backwards along our function and see that as we get to 0, we're going to have 0 from the right-hand side. Now, this, as you can see, there's two different answers here, and this is why over here the limit as x approaches 0 of this function does not exist. It's because the left-handed limit and the right-handed limit do not equal each other. So now, what is f of 0? Now, f of 0 would be equal to 0, as this closed circle shows. So f of 0 equals 0, and f of -1, right here, would end up being -1. As you can see, it's different. The limit as x approaches -1 from the right hand and the left hand is -2, but f of -1 is equal to -1. Now that we know how to solve limits graphically, we're going to learn how to solve them algebraically. So there's 3 different methods on how to solve limits algebraically, and they're up here. The first one is to simply plug it in. The second one is to simplify and then plug in. And the third one is what we call the think hard method. So first we're going to go over the easiest of the 3, the plug-in method. So let's start with the equation limit as x approaches -1 of x squared minus x all over x squared plus x minus 2. So with the plug-in method, we're going to take whatever the limit is approaching, in this case it's -1, and we're going to just simply plug it into this function. So it's going to be -1 squared minus -1 over -1 squared plus -1 minus 2. As you can see, all we did is plug in -1 wherever there was an x in the original equation. So that's going to equal 1 plus 1, 1 over 1 minus 1 minus 2, which gets you 2 over -2. So the limit of this, limit as x approaches -1 of all of this, is equal to -1. And that's the answer. So to backtrack, all we did was plug in what we were approaching, x equals -1. Wherever there's an x in the original equation, we've simplified it all the way through, and we ended up getting that the limit of this function as it approaches -1 equals -1. Now, with this next one, we're going to try the plug it in method to see if it works. Since that's the easiest one, you always try it to see if it works first. So we're going to just plug it in. So we're going to get -2 squared minus 5 times 2 minus 14 all over -2 squared plus 5 times 2 plus 6. Now when you do all this out and simplify, you're going to end up getting 0 over 0. That's not our final answer. When you have 0 over 0, it means that you need to try to simplify the equation. We need to try to use another method, whether it be simplify or the think hard method. So we're going to do the simplify method for this. So what we're going to do is we're going to factor. Now, in factoring the top, we're going to get the limit as x approaches -2, and we're going to carry this with us because we haven't actually taken the limit yet, of x plus 2 multiplied by x minus 7 over x plus 2 multiplied by x plus 3. So in this case now, what we can do is we can cross out the x plus 2's because they're going to cancel each other out, and we're going to end up with just x minus 7 over x plus 3. And it's at this step right here that we're going to revert back to number 1, which is plug in. So now, the limit as x approaches -2 of x minus 7 over x plus 3, we're going to go and we're going to plug it in. So -2 minus 7 over negative 2 plus 3, we're going to end up getting negative 9 over 1. So our answer will be negative 9. Now we're on to the third and final method of solving algebraic limits. So with this, we're giving the equation the limit as x approaches 4 of square root of x minus 2 over x squared minus 16. This in the end will give us 0 over 0. We can't simplify it because you can't factor at the top. Therefore, we are on to the think hard method. So with this, what we're going to do is we're going to multiply by what's called the conjugate. So we're going to multiply by the conjugate, which is going to be the square root of x plus 2 over the square root of x plus 2. The reason why we multiply it by the same thing over the same thing would be because you have to multiply it by 1. So we're going to get, after all of the multiplication and everything, we're going to end up with x minus 4 over x squared minus 16 multiplied by the square root of x plus 2. Now we can go back to our second rule of simplifying. So we're going to take the limit as x approaches 4 of x minus 4 over x plus 4, x minus 4, and then the square root of x plus 2. So as you see, we reverted back to our second rule in simplifying, and we simplified this to get x plus 4, x minus 4. Now, that we've simplified, we can get rid of the x minus 4's, and we're going to just write it as 1 over x plus 4 square root x plus 2. So we're going to end up with this. So now, the limit as x approaches 4 of 1 over x plus 4 multiplied by the square root of x plus 2. We're going to go back to our first method of just simply plugging it in. So I'll just circle this one back here and say we went back to number 2 of factoring or simplifying. Okay, so now when we plug it in, we're going to get 1 over 4 plus 4 multiplied by the square root of 4, which would be 2 plus 2. So we're going to end up with 1 over 8 times 4, which would be 1 over 32, which would be our answer. So these are the 3 different ways. You can simply plug it in if it works. If not, try to simplify by factoring it and then revert back to plugging it in. And then the third one would be to think hard and figure out how to manipulate the algebra in order to be able to factor it or plug it in.